Hi guys, let's take a look at the preparation for exam 3. This is my favorite test of the semester. I love the material in this section. We're starting off with problems 1 through 5. They're all chain rule problems. They should come directly from section 3.7. Before heading into those sections, please do notice the instructions that I have on this practice test will be the same as the instructions on the actual test. So whenever you're taking this test for me, I don't want anything other than your name written on the test page. So don't write anything on your test page. It's just going to be used as a cover sheet for your work when you're done. You're going to do all of the problems on your own paper, hopefully in order to make it easier for me to grade. Show as much work as possible for credit. And there's only 2 problems in which you'll be able to use logarithmic differentiation. So I say only use logarithmic differentiation when you are told you may. Now remember, logarithmic differentiation is when you take the natural log of both sides of your equation before you start taking the derivative. So the problems where you can and should do that are 14 and 15, but you shouldn't do that on any other problems. And because I do think that this test is a little long and a little hard, I'm going to give you the benefit of only dividing however many you have correct by 22, even though there's 23 problems on the test. So you could make, with a perfect test, 23 out of 22, which would give you a 105 for the grade on the test. That'd be pretty awesome. Okay, let's go ahead and look at how you would do that if the test were like this practice test. Okay, so first problem here. And in fact, I think I'll go ahead and move that out from underneath. First problem, we have f of x is equal to 1 over the cube root of x squared plus x plus 1. First thing I did when I was trying to work that problem is I said, well, I know I'm going to have to think of that, whether I write it or not, I have to think of that as the group x squared plus x plus 1 to the negative 1/3 power. 1/3 power because it's the cube root, and the negative 1/3 power since it's the cube root in the denominator. Now, that makes it easier to take the derivative. So I just say, well, that 1/3 comes down in front, and then I would have the group to the negative 1/3 minus 1 power. That's where the negative 4/3 comes from. Now, the power rule is the derivative of the outside of that group. Chain rule says now you need to multiply that by the derivative of the inside. And I can say, well, derivative of the inside here is just going to be the derivative of x squared plus x plus 1. Derivative of x squared is 2x. Derivative of x gives me my 1. Now, this would be my final derivative answer here. I just wanted to make it look nicer. The original problem was written in radical form, so my answer really should be in radical form. I need to understand that this negative 4/3 power means the cube root of this group to the 4th power in the denominator. So that was the first thing I did. I said the cube root of that group to the 4th power in the denominator. I knew negative 1 was a factor in the numerator. The only other group that belongs in the numerator is this group. So you'll see I said negative 1 or just a negative times the group 2x plus 1. And your factor of 3 from the 1/3 goes in the denominator, multiplying that cube root. Beautiful final answer there. For the next one, it's a similar type of question. You have t minus 2 over 2t plus 1 raised to the 9th power. So when I'm looking at that, I can say, well, all right, again, I have to take the derivative of the outside. Derivative of the outside, power rule. 9 comes down in front times the group to the 8th power. And then I can say, okay, once I do that, then I have to say the derivative of the inside. This time, the derivative of the inside can only be taken if you use the quotient rule. So I went in and I said, okay, I'll square the denominator, bring the denominator to the numerator, multiply it by the derivative of the numerator. But the derivative of t minus 2 with respect to t is just 1. And then I said, okay, that's the denominator times the derivative of the numerator minus the numerator, t minus 2, times the derivative of the denominator, which again, with respect to t, that derivative is just 2. I knew that I would really like to simplify this, and I didn't want to show a whole bunch of steps. So in red, I just went ahead and simplified in this step what that numerator would be. Your first group is going to be 2t plus 1. You're going to be subtracting the product of 2 times t minus 2. So you're subtracting 2t, and you're actually adding 4 since it's minus a negative 2 times 2 for plus 4. So then I can say, well, okay, I can see I'll have 2t minus 2t. The t's cancel in that numerator. So that numerator is really just 1 plus 4. It's a factor of 5. So what I did is I said, well, I'm going to take the factor of 5 there, multiply it by the factor of 9 that I have out front. I understand that that 9 also is a factor in the numerator because that 9 could be written as 9 over 1. So 9 times 5 is 45. And then I have times the group t minus 2 to the 8th power. And then in the denominator, please notice you have a 2t plus 1 to the 8th power times a 2t plus 1 to the 2nd power. Well, when you multiply those, you're going to get 2t plus 1 to the 10th power. Pretty cool problem. And again, the derivative part was here. I just simplified it to this nice factored answer over on the end. And in number 3, I specifically say you must have a factored answer, and a factored answer completely from the problem given. So it's not enough just to take the derivative, especially in number 3. I need a nice factored answer. Okay, so we start off with the product, 2x plus 1 to the 5th times x cubed minus x plus 1 to the 4th. When I take the derivative of that first one, the 5 comes down in front of the group, times the group to the 1 lower power. Well, 5 minus 1 is 4. That's the derivative of the outside of that first term. Times the derivative of the inside. Well, the derivative of 2x plus 1 is 2. All of this is the derivative of the first. Now, times the second, plus the first, 2x plus 1 to the 5th, times the derivative of the second. And for that, the 4 has to come down in front, times the group, raised to the 3rd power. And then this is the derivative of the inside of that group. I get the 3x squared minus 1. Now, at that point, I wanted to factor. I think all of this is my first term. All of this is my second term. And I have to consider what's the greatest common factor between those two terms. Well, notice in the first one, it has constant factors of 5 times 2. My second one, it only has one constant as a standalone factor of 4. I can factor a 2 out of both of them, so that's what I did. Up next, they both have the group 2x plus 1. I can factor out 2x plus 1 raised to the 4th power. And they also both have the cubic x cubed minus x plus 1. I factor out it to, again, the lower power. Greatest common factor always factors out the lower power of 3. Now, whenever you factor that out, what I had left in the first group, I still had a constant factor of 5 left in that first term. So that had to go, or that had to be put down, I should say. The 2x plus 1 to the 4th factored out completely. The 2 is gone. The group x cubed minus x plus 1, I didn't factor all of it out of the first term, so it has to stay in there. And I'll have 5 times that trinomial, x cubed minus x plus 1. Now notice it's, of course, just to the 1st power. For my second term, I factored a 2 out of the 4, leaving me a constant factor of 2. The group 2x plus 1 needed 1 power left because I had the 5th power here and I'm only factoring out the 4th power. The trinomial x cubed minus x plus 1 completely factored out of the second term. And of course, I also have the group 3x squared minus 1 that does have to be accounted for here since it didn't factor out. So everything I have in black is what's left in the two terms after you take out the greatest common factor. This is still not a final answer, though, because you never want any multiplication unless the terms are factors. So these terms are factors, these terms are not factors. I undid the multiplication that I have here in the red above. I distributed the 5 through this group, and what I did over here is I just FOILed out 2x plus 1 times 3x squared minus 1, and then I took each of my answers and multiplied by 2. So like 2x times 3x squared is 6x to the third times 2 is 12x to the third. Then my next term here, I would have plus 1 times 3x squared is 3x squared times 2. That gives me a 6x squared. Then I take a negative 1 times each of these two terms. Negative 1 times 2x is minus 2x times 2 is minus 4x. Negative 1 times 1 is negative 1. Multiply that by 2 and you get your negative 2. So that red is just where I distributed all of that out. Now my final factor had to be simplified. All I did is I collected like terms. 5x cubed plus 12x cubed is 17x cubed. For the x squared terms, there was only the one of them, the 6x squared. Then you had minus 5x minus 4x for minus 9x, plus 5 minus 2, plus 3. And at that point, along with our other factors, this is my fully factored final fantastic form of the answer there. That's a good problem. The next few are much shorter problems, but you do have to make sure that you're using the chain rule correctly in them. And number 4, please make sure you understand that you see that this is a differentiable function, the tangent of x, inside of a differentiable function, the cosine of x, inside a differentiable function, the sine. So you say, well, okay, that means that there has to be 3 layers to your chain rule derivative. And as long as you account for them, you should be fine. So the 3 layers, I can say, well, the outer layer is what must be done first, the derivative of that sine function. Well, derivative of sine is cosine. And then remember, you leave the angle alone. So the first layer of the chain rule takes the derivative of the outside, leave the inside alone. So cosine of the cosine of the tangent. Now you're multiplying by the derivative of what was inside of that. So now you're saying, okay, now I'm looking at this. Derivative of cosine is negative sine. So I multiply by a negative sine, leave the angle, tangent x. And now, since that's a negative sign, you don't have to have the multiplication sign, but you would at the very least need a parentheses around this. Otherwise, it would look like the cosine of the tangent minus the sine of the tangent. So in order to make that not look like a minus, you have to have parentheses around it. And then you're still not done. That's the second layer of the chain rule. Last layer of the chain rule, you have to say, well, now I need to multiply by the derivative of what was inside of that. What's inside is a tangent, and we know derivative of tangent is secant squared. Okay, that's it for that problem. Now for the next one, again, we have a differentiable function, 3 theta, inside of a differentiable function, the secant of theta, inside of an exponential function. So again, this one has 3 layers, but the first layer is kind of boring, where you say, well, derivative of any exponential function is that exponential function. That's the first one. Then you say, okay, times the derivative of what was inside of it. Well, what's inside of it is a secant, and we're supposed to remember derivative of secant is secant tangent, and you have to put that angle with each one of them. So we say, okay, times secant 3 theta, tangent 3 theta, not done, times the derivative of what was inside of that secant. And you say, well, the derivative of 3 theta is going to be 3. This would be a fine way to leave your final answer. You could move the 3 out in front of your exponential function, but perfectly fine with it like this. For the next problems, now, number 6 starts section 3.8 on the test. This is where we're doing implicit differentiation, and 3.8 also gets into your logarithms and logarithmic differentiation. We're starting with the implicit differentiation problems. For number 6 here, I give you the relation x cubed plus y cubed is equal to 6xy. So we say, okay, how do we work with that? First of all, take the derivative of the left-hand side. And please notice, nowhere in this problem am I saying dy dx is equal. That's bad. Dy dx reveals itself as you're taking the derivative of this problem. So it's not like these earlier problems where I could say y prime equals g prime of t equals. If somebody said y prime equals and then started taking that's wrong in this problem. You cannot do that. In a relation, the dy dx shows itself as you start taking the derivative. So I'll say, okay, derivative of x cubed is 3x squared. The derivative of y cubed, and remember that's really 3x squared times the derivative of the inside, which would be dx dx. We don't put that since it's just a factor of 1. Now, the 3y cubed is different because we say, well, we will put it this time for the derivative of the inside. Derivative of the outside, 3y to the second, times the derivative of the inside. We're taking the derivative with respect to x, so it's dy dx, which is precisely what I'm solving for. So now I move to the right-hand side, and please keep in mind you're going to have to use product rule on it. You have the differentiable function 6x times the differentiable function y. So I'll say derivative of the first is 6 times the second, plus the first, 6x, times the derivative of the second, dy dx. Now at this point, I know I need to solve for dy dx. So the first thing I do is I say, I'm going to move every dy dx term to the same side. 9 times out of 10, I choose to make that side the left-hand side. So in this case, just like I normally do, I'll move the dy dx to the left. At the same time, I went ahead and factored it out. I said this term had a dy dx, so it'll stay on the left-hand side. When I factor the dy dx out, I'll have 3y squared. When this term moves over, it's going to become a minus 6x, again, after you factor out the dy dx. The terms without a dy dx move to the right, which is just the 3x squared. When it moves to the right, it becomes a minus 3x squared, subtracting the existing 6y that was already on the right-hand side. Now, dy dx times this group is equal to this group. So I can say, well, then dy dx is equal to what was on the right, 6y minus 3x squared, divided by 3y squared minus 6x. I would have been happy with this answer, but generally I like answers fully simplified. So I'll go ahead and say I can see that there is a greatest common factor of 3 in the numerator and denominator. Then those three canceled, those three factors of 3 canceled. So you're left with the answer 2y minus x squared over y squared minus 2x. Good problem. Now, if that's a good problem, the next one's a great problem. Love it. So this time, yes, you have an implicit differentiation relation in terms of x and y, but now you've got an x and y term inside of your sine function that you're going to have to take the derivative of. So you have to think, again, chain rule on that left-hand side. So you say, okay, derivative of sine is cosine. Keep the angle. So I get cosine, keep the angle x plus y. Now chain rule says times the derivative of the angle. Well, if I go in there and say, well, it's the derivative of x with respect to x, that's a 1, plus the derivative of y with respect to x, I just have to leave dy dx for that term. Now on the right-hand side, it's a product. So derivative of the first is going to be 2y dy dx times the second, cosine x, plus the first, y squared, times the derivative of the second. Derivative of cosine is negative sine. So then at that point, I can say, well, okay, I need to move all my dy dx terms to the same side. In order to make it easier to see which terms had the dy dx, though, I went ahead and showed that this cosine of x plus y was multiplying both terms in this expression after it. Cosine x plus y multiplies a 1. I get, of course, cosine x plus y, but then it also multiplies the dy dx, and I'll get cosine x plus y times dy dx. So I had 2 terms on that left-hand side. I just left my right pretty much the same, except I put the dy dx at the end of the first term. Order of multiplication doesn't matter. And I went ahead and instead of saying y squared times a negative sine x, I just called that minus y squared sine x. Now, at that point, I would like to move every dy dx term to the left, so I'll go ahead and factor it out. When I factor it out, I can see I already had the cosine of x plus y term on the left. I move the other dy dx term to the left, and it becomes a minus 2y cosine x. On the right-hand side here, we already had the negative y squared sine x, so I just moved that to the front. And then this cosine x plus y has to move over. When it does, it becomes a minus cosine x plus y. So dy dx is equal to what was over here on the right-hand side divided by what was previously multiplying it, and nothing factors or cancels in that expression. That's our fully factored and fantastic final form of the answer. For the next problem that's dealing with implicit differentiation, and the thing that makes this one nice is anytime I ask you to find the second derivative of an even relation such as this, in order to get to the final answer, you're going to have to not only plug the first derivative into dy dx into the second derivative, because you don't want to define the second derivative in terms of the first derivative. But not only are you going to have to plug the first derivative in, but you're going to have to go back and plug the original relation in to your simplified second derivative in order to get to the final answer. And that's kind of a nice thing, because whenever you can see, hey, the original equation goes back in this problem, that's guaranteeing you that you've done it correctly. Okay, so now with this problem, we have x to the fourth plus y to the fourth is equal to 16, and we're supposed to find the second derivative. So first derivative of x to the fourth is 4x to the third. Derivative of y to the fourth is 4y to the third times the derivative of y with respect to x. We know derivative of any constant, 0. Now, what I did is I said, well, that 4x cubed moves to the right-hand side, and it would become a negative 4x cubed. Then I would have to divide it by the coefficient of dy dx, 4y cubed. So the right-hand side is going to become negative 4x cubed divided by 4y cubed. You can make these problems a lot simpler on you if you'll go ahead and cancel out the factor of 4 here. Usually in these problems, something will reduce in the first derivative, and you should reduce. It makes it easier. I'll have a negative x cubed over y cubed after reducing that down. Now, we already know what the first derivative is. We need the second derivative. I went ahead and did my second derivative up here. Since the first derivative is a quotient, we have to use the quotient rule to take the second derivative. Quotient rule tells me to square the denominator, then bring that denominator up to the numerator, times the derivative of the numerator. Derivative of negative x cubed is negative 3x squared. Then we say, okay, at that point, we subtract the numerator, negative x cubed, times the derivative of the denominator. Derivative of y cubed is going to be 3y squared dy dx. At that point, I knew that dy dx, I don't want to define the second derivative in terms of the first derivative. That would be like looking up the definition of a word in the dictionary and using a different tense of that word to describe it. So I go ahead and I can say, well, dy dx is this. I substitute that in the next step. So I say must plug what dy dx is equal to in its place. The only other thing I've done here is rewrite and simplify a little. That first term is negative 3x squared y cubed. And then that minus a negative becomes plus a positive. And I'll have 3x cubed y squared times dy dx, which is negative x cubed over y cubed. All of this is over y to the sixth from that y cubed squared. Remember, y to the third raised to the second, power to power, you always multiply. So I have a y to the sixth in the denominator. Now, I decided I wanted to simplify, and I had to simplify, but the easiest way to simplify is to multiply by the least term that you need. So I could see some people, I don't want to say making a mistake, but they might say, well, I need to multiply by y cubed over y cubed. No, you don't, because this y cubed that you're dividing by in the problem, it's already multiplied by y squared. So I really only have a fraction with a y in the denominator there. So I'll get rid of that fraction. We don't want to have fractions within a fraction. It's a compound fraction. So in order to get rid of that, we multiply by y to the first in the numerator, and that along with the y squared term is going to get rid of that y cubed that you're dividing by. But you can't multiply the numerator by y unless you also multiply the denominator by y. So I do that. That's where the y to the 7th came from in the denominator. In the numerator, when that y distributes to both terms here, the first term you're going to have negative 3x squared y to the 4th when you multiply it in. In the second term, again, all of the y's just cancel, and you're going to end up with 3x cubed times a negative x cubed. That gives me negative 3 or minus 3x to the 6th. Okay, so I'm feeling pretty good about this answer at this point, and I can say, yeah, but I haven't plugged in the original relation yet. How do I get to a point where I can do that? After you've simplified your derivative, make sure you factor it. So look at this numerator. You can see it has a common factor of negative 3 and a common factor of x squared. I factor that out. When I do, my first term is y to the 4th. My second term would be plus x to the 4th. And remember, order of addition doesn't matter if it's y to the 4th plus x to the 4th or x to the 4th plus y to the 4th. We know that that is equal to 16. Then that's the instant where we know, yeah, we have this problem, because we can plug the 16 in for that original relation equivalency there and say this is just negative 3x squared times 16, which gives me negative 48x squared over y to the 7th. Wonderful problem. Now, the rest of the 3.8 problems get into your inverse trig and logarithmic functions. So we're looking at, well, actually just the inverse trig, then logarithms, that's actually a 3.9 section. So another 3.8 problem would be number 9 on our practice test and test. I give you a problem that says 3x inverse sine of x squared. So in addition to the inverse sine, which please do remember, the derivative formula for inverse sine is 1 over the square root of 1 minus x squared. You've got to know that. Derivative of the inverse tangent is 1 over 1 plus x squared. Derivative of inverse secant is 1 over the absolute value of x on the square root of x squared minus 1. All of those are in your notes. All of those are needed for the test. So in this one, in addition to knowing how to take the derivative of inverse sine, I had to realize this is a product rule, because I have the differentiable function 3x times the differentiable function, the inverse sine of x squared. So I said derivative of the first, derivative of 3x with respect to x is just 3, times the second, plus the first, 3x, now times the derivative of the second. Well, the inverse sine formula says to say it's, or says to take the derivative by putting 1 over the square root of 1 minus whatever's inside of the inverse sine function squared. So it's 1 over 1 minus the quantity x squared in this problem. And then this part right here, that's the chain rule. You're saying times the derivative of what was inside of that, derivative of x squared is 2x. Now to simplify this, the first term, there's nothing to do with it, 3 inverse sine of x squared. Second term, you can certainly simplify. The numerator is going to be 3x times 2x for 6x to the second. Your denominator, you're going to have the square root of 1 minus x to the 4th. That would be our nice final answer, and you can't combine the terms there. Those are not like or anything like that. So I would just stop at that point and say, good answer. For the next one here, we have the inverse tangent. It's just the inverse tangent of theta to the fourth power. So there's no product or anything here, but there is chain rule going on. So I can say, all right, the inverse tangent formula tells me to say that the derivative of the inverse tangent is always 1 over 1 plus whatever's inside of it squared. In this case, it's 1 over 1 plus theta to the fourth squared. And then the chain rule says multiply by the derivative with respect to theta of what's inside. That's theta to the fourth. Its derivative is going to be 4 theta cubed. Final answer here, that 4 theta cubed belongs in the numerator here, and it's going to be 4 theta cubed over 1 plus theta to the eighth. Theta to the fourth raised to the second, theta to the eighth there. Now, that would end section 3.8. Section 3.9 talked about logarithms and exponential functions. And we say, well, okay, so in looking at this, what if we have log base 5 of the natural log of x all raised to the fourth power? So the tricky thing here is, yes, this problem has logarithms, but it also is, again, a chain rule problem. We have a differentiable function inside of a differentiable function inside of a differentiable function. So you have to have 3 layers to your derivative here. You say, okay, 3 layers. The outermost layer, the outermost of this group, it's the power. So take the derivative using the power rule. That means the power 4 has to come down in front times the group left completely alone, raised to 1 lower power. Now it's to the third. This is the derivative of the outermost term in the group. Then you say, okay, now times the derivative of the inside. Well, the inside function is a log base 5. So I can say, well, derivative of any logarithm is 1 over what's inside of it. So I say 1 over natural log of x. Now, anytime you have a log of any other base other than the natural log, you also have to divide by that natural log of this base. So all of this is in the derivative of the log base 5. Derivative of the log base 5 of any term is 1 over that term times the natural log of this base. And then the final thing you have to do is say, yeah, but chain rule says we need to multiply by now the derivative of what was inside of that. Derivative of the natural log of x is 1 over x. And since that's understood to be log base e, there's no sense to put natural log of e after it. It wouldn't be anything other than a factor of 1. So now this would be a nice answer. I just cleaned that answer up over here, and I showed, well, your numerator is going to be this 4 times the group log base 5 of natural log of x raised to the third power. And then all of these terms are in the denominator, so I wrote the denominator as x natural log of x times the natural log of 5. Final answer there. Now for number 12. In number 12, we're looking at one where we're, again, taking the derivative of a logarithm. This time, again, it's also a 3-part chain rule. You have a differentiable function inside of a differentiable function inside of a differentiable function. So as we're doing these, just like in the last problem, you needed to see that there was 3 components to the derivative. Component 1, component 2, component 3. There has to be 3 components to this derivative. When I'm doing that, I'm just saying, well, okay, it's component 1, component 2, component 3. And in that component 1, I really needed to put a 1 in that numerator here. I'll fix it there and say, okay, now for the first part, derivative of any logarithm is always going to be 1 over what's inside of that logarithm. So I can just say, well, it's 1 over the tangent of the natural log of t. But then the chain rule says you need to multiply by the derivative of what's inside. I could have went ahead and put the derivative of what's inside up in the numerator. I chose to put it out beside just to show you this is the first level of your chain, second part of your chain, third part of your chain. Second part of your chain is the derivative of what was inside. Derivative of tangent is secant squared. I keep the angle, natural log of x. Finally, you say, well, times the derivative of that angle, derivative of the natural log of x, 1 over t. So then I cleaned up my answer and said, this is nothing more than secant squared of the natural log of t divided by t times the tangent of the natural log of t. That answer is a nice final answer. For the next one here, number 13, we have a nice exponential function. And what I need you to remember about exponential functions, the derivative of any exponential function is that exponential function times the derivative of its exponent, always times the natural log of its base. That doesn't come up too often because most of the time we're taking derivative of exponential functions. Our exponential base is e, so we don't have to worry about it. So like, for example, back when we worked problem 5, over on this page, I just said derivative of e to the secant of 3 theta is e to the secant of 3 theta times the derivative of the exponent, secant 3 theta, tangent 3 theta, times the derivative of the angle 3. That's all that was needed. Now, I could have put out beside this times the natural log of the base. You're like, well, but again, you'd be wasting your time if you did that because the natural log of e is just a factor of 1. So it's better not to do it in that problem. But you could think of it, you always do that. So it's just, in that case, it's better to not show it. But I didn't want you to think that I'm changing the rules here. The rules are always the same. So if I take the derivative of 5 raised to the x to the 4th, derivative of any exponential function is that exponential function times the derivative of its exponent times the natural log of its base. In this case, I have to put natural log of 5 because that's not just a factor of 1 like the natural log of e would be. So that would be my final answer there. Now we get to the problems in which I will tell you on the test. Now I say may use logarithmic differentiation. Let me strongly urge you that you should use logarithmic differentiation. Not saying that, well, and in fact, in 15, there's no way to get to 15 unless you use logarithmic differentiation. But in 14, there's you could do a ridiculously long quotient rule problem and get to it, but it would not be the wise way to work the problem. 15, there's no way to get to the solution without logarithmic differentiation. So looking at 14 here, we do have y set equal to this quotient, x squared, x plus 2 to the 3rd, times sine squared x over 2x plus 1 to the 5th, 3x plus 2. Now, the nice thing about taking the natural log of both sides is that it's going to enable you, anytime you have a natural log, we can do logarithmic expansion. You can say, okay, whenever I expand, if terms are inside of a logarithm, then any term that is multiplied, it's going to be separate logarithmic functions, and you're going to be adding them together. Any power on a term comes out as a coefficient on that individual logarithm. Any terms that's being divided, you separate them by subtracting them. So that right-hand side, please make sure you see that whenever I take the natural log of it, the expansion is going to give me 2 natural log of x, because natural log of x squared is better written as 2 natural log of x. The next term, the 3 comes down in front of its natural log, and I get the natural log of x plus 2. Then plus 2 comes down, natural log of the sine of x. Then anything in the denominator is always minus. The 5 come out in front of this one, minus 5 natural log of 2x plus 1. And then my last term, minus, again, because it's divided, anything in the denominator is going to be minus the natural log of 3x plus 2. Okay, so I have my logarithmic expansion there. Please remember, no derivative has been taken yet. Sometimes students get confused and they start thinking when they move the exponents down in front that they're taking the derivative. You're not. All we're doing at this point in the problem, that's just pre-calculus logarithmic expansion. Now we need to take the derivative. Derivative of any natural log is 1 over what's inside the natural log times the derivative of what's inside the natural log. So my left-hand side becomes 1 over y dy dx. On the right, I'm going to have 2 times derivative of the natural log of x, which is just 1 over x, plus 3 times the derivative of natural log of x plus 2, which is just 1 over x plus 2. My next term, I have plus 2 times the derivative of the natural log of sine of x. So I said, okay, when I take the derivative of the natural log of sine of x goes in the denominator. Now you could say it's 1 over sine x times the derivative of sine x. The derivative of the denominator always ends up in the numerator eventually. So you can save yourself the effort and just say, okay, put the sine in the denominator. You know the numerator is going to end up being the derivative of the sine, which is cosine in this case. Same thing in the next one. I said minus 5, and then the derivative of the natural log of 2x plus 1. 2x plus 1 goes in the denominator. The derivative of 2x plus 1, 2, goes in the numerator. Then the last one, we have minus derivative of the natural log of 3x plus 2. 3x plus 2 goes in the denominator. Its derivative 3 goes in the numerator. So I've taken the derivative at this point. I want the final answer, though, solely in terms of x. So you say, okay, then dy dx, you would have to multiply y on both sides. Since I want the answer in terms of x, though, you can say, well, y is just your original function. So dy dx is going to equal the original function times this expression that we just had. And that simplified to be 2 over x plus 3 over x plus 2 plus 2 cotangent x minus 10 over 2x plus 1. And then the last term didn't simplify, just minus 3 over 3x plus 2. Okay, I'll stop the Zoom at this point just to make sure that it doesn't cut me off, and I'll do another video for the remaining problems.